Can you see the slides at home? Yes? No? Now I see. Let me check. Yes, okay. We can start. General anesthetics. Why this class of compounds in our program? You will see that general anesthetics are very simple molecules. In the past, chloroform and the ethyl ether were used as general anesthetics. But it is important that you know the effect of this molecule on our body. Perhaps if you work in a lab and then the atmosphere is saturated by this type of compounds or by other gaseous organic compounds, it is possible to have a decrease in attention and perhaps the appearance of sleepiness. And so it is important to know the effects of these compounds on our body. This type of compounds are CNS depressant drugs. Once again, these compounds are able to modulate the GABA receptor, in particular GABA A receptor. These compounds are able to cause partial or a complete loss of pain sensation, together with a loss of consciousness, and lead to a stage, to a plane of anesthesia. So you sleep, you don't feel any pain, and so the doctors can work freely without any reaction from you. We can divide anesthesia in different phases, stage in French, or plans. The first step, the first phase is called analgesia. In this case, there is only a moderate depression. This type of this phase is useful, for example, for very light, for minor intervention, for example, on the skin, on very superficial. It is not required a pronounced muscle relaxation, because the doctors need a complete relaxation of muscle to cut the muscle to reach the organs and to work freely and without any problems. This is the first step, very easy to reach. Perhaps you have already, you know this phase because it is sufficient to drink some alcohols, and then you can reach very easily this first level of anesthesia. The second level is called delirious. This means that at this point you have no more influence from your willing. So at this level you can respond to any questions, you can answer to any questions. You see there is an increased disinhibition. In this case, there is also an excitation of involuntary movements. No control on the movements. And this is the second level, which corresponds to an increased concentration of anesthetics. The third level is represented by surgical anesthesia. This is the most important level. And this level is divided in other subclasses, subplanes. You see A, B, C, D. A, loss of spinal reflexes. B, reduction of muscular reflexes. C, paralysis of intercostal muscles. And D, disappearance of muscle tone. The doctor should check very carefully the concentration of anesthetics in order to avoid to reach the last phase. You see the disappearance of muscle tone, and at this level corresponds a respiratory paralysis. This means that the muscle dedicated to the respiratory act are blocked. And so it is necessary the assistance with a mechanical equipment in order to avoid the death. So it is important to know your weight, because the dose of anesthetics correspond normally to the weight of the patient. There is a special table, just to know the right quantity of anesthetics. You see in this table these 4 phases: stage 1, analgesia; stage 2, delirium; stage 3, surgical anesthesia; and stage 4, respiratory paralysis. Stage 4 corresponds to the toxic quantity of barbiturates, for example. Barbiturates are also able to give respiratory paralysis. Also, drugs from morphine are able to give this effect, this final and severe effect. You see medullary depression, respiratory arrest, cardiac depression and arrest, no eye movement. The first two periods, the first two phases are called also induction of anesthesia. Because during this period, the subject assume the right quantity of anesthetics, but at the beginning, the anesthetic should reach the CNS, the brain. And so at the beginning, you see the phase, the anesthesia is not a sudden effect. So it appears very, very slowly. And it is important that this substance, these anesthetics, should be not irritant on the mucosae, on the respiratory tract and so on, to avoid any other effect. The classification of anesthetics is based on their route of administration. So we have 2 classes: inhalation anesthetics and parenteral parenteral and intravenous anesthetics. So liquid or gaseous. Here in the table, you can see the qualities which should have an ideal anesthetic. For example, rapid and pleasant induction of surgical anesthesia. Rapid and pleasant withdrawal from surgical anesthesia. Adequate relaxation of skeletal muscles, potent enough to allow adequate oxygen supply and mixture, wide margin of safety, non-toxic, absence of adverse effects, non-flammable and non-explosive. We'll see that this point is very important because several gases are flammable, and some vapors can be explosive. Chemical compatible with anesthetic devices, non-reactive and inexpensive. Okay. The first problem of this class of compounds was related to the chemical stability. Why? Because one of the first anesthetics was diethyl ether. You have studied this compound in organic chemistry. You know it's a very simple compound. Perhaps I can show you the chemical structure, just a moment. Okay. Here. Okay. Here. Okay. So, if you know, diethyl ether is very, very simple. You see an oxygen in the middle, CH2, CH3, CH2, oops. Very, very simple. But, and this compound is not toxic, should be the ideal anesthetic. But it has a problem. Flammable. Why flammable? This quality is a problem. Because you know that surgical tools should be sterilized. And in the past, the sterilization was carried out by flame, a free flame. And so you have a flame very close to a flammable solvent. And this was the cause of accident during the surgical intervention. But ether has also another problem, is explosive. Why? It is possible the formation of a very reactive derivative, ether. We see here, just a moment, there is, oh, you can see here. Out. doesn't work. Just a moment. Okay. This one. I share the slide. Just a moment. Okay. It's possible the formation of peroxides, ether peroxides. And these peroxides are explosive. So we have a good anesthetic without severe side effects, important side effects, but it is flammable. It is explosive. So, in theory, we have to change the chemical structure of ether in order to improve its safety. It is possible, yes. There is another compound used in the past called chloroform. So chloroform is very simple. Oh, sorry. So. Chloroform is inflammable. It derives from another well-known compound that you know. Oh, sorry. Methane. Methanic explosive, flammable. We replace some hydrogen atoms with halogens, and then we get chloroform unflammable. This should be the right approach. I can insert some halogens on the chemical structure of ether in order to change its chemical-physical properties. In particular, I can transform a flammable compound into an unflammable compound by inserting some halogens and by retaining the backbone of ether. An ether backbone with halogen atoms on the chemical structure. This suggestion comes from the transformation of methane in chloroform. Chloroform is not in use. Why? It's a cancerogenic agent. Very good as an anesthetic, but toxic. So we have two situations. A good anesthetic but flammable, another good anesthetic but toxic. So we can put together the properties of both, and then you will see, we have the modern, the more recent anesthetics. But please remember, you know ether, you know chloroform, we can put together the insertion, the replacement of the hydrogen on the ether to give the new recent anesthetics. So, once again on the slides, okay, here. There is another important point. The solubility of gas in water. Why this point is important? We'll see. It is important to saturate the blood with a gas in order to reach the CNS. But please, we can see together this brief movie. Just a moment. Okay, include the audio. It doesn't work. I don't know why. Okay, but I see this movie. Doesn't work? No. Perfect. Just a moment. Oh, okay, doesn't work. The problem is the solubility of a gas in water. If you see on the bottle of mineral water, you see that the mineral water can contain gas, some gases. CO2, oxygen, other gases. Because gases are soluble in water. So, if we assume some gases from an external source, these gases can be solubilized in our blood. And only after the complete saturation of the blood, we have the release of this gas to the CNS. So it is important a complete saturation of the blood by this gas. 1, 2, 3. If we want the release of this gas into the brain to reach the different phases of anesthesia. So another important value, flammability, toxicity, is also the solubility of a gas in our blood. Blood, you know, like in water, because blood is formed by more than 70% of water. Because the solubility can influence the time to reach a complete anesthesia. The induction time is called. If you want to reach the third phase of anesthesia very quickly, you need a gas with a very low solubility in blood. Why low solubility? Because with a low soluble gas, you reach the saturation very, very quickly. You can understand. If your gas has a higher solubility in water, you need much more time to reach the complete saturation of the blood. And you need more, an increased quantity of the more soluble gas. This is important for the induction. So it is important to have a low soluble gas, low soluble, water soluble gas, to have a quick induction. You see here in this picture, at the beginning, inhaled and exhaled gases with the respiration, but in particular for induction, we are interested only on inhaled gas. Gas is able to reach the alveoli, and then you see an equilibrium with the blood. And the blood, after its saturation, is able to release the gas in all tissues, in all body, including brain. What happens at the end? It is necessary, you see all these steps are an equilibrium, and so it is necessary to come back, and then from the brain to the blood, complete saturation of the blood, and then alveoli, and then exhaled gases. If you want to have a quick elimination of your gas from our body, it is necessary a low soluble gas. So one of the main property of an ideal anesthetics is its solubility in blood. In particular, here in this table, you can see the partition coefficients. So the ability of a gas to be soluble in water and in oil. So you have a situation with these two substances, oil on the surface and water, and then you can bubble your gas inside this system, and then we can measure the concentration of the gas in the two phases, and then we can determine, we can have a number about the solubility of the gas you see in the blood or in the oil phase. As I told you before, the best anesthetics are characterized by very low solubility in blood. You see nitrous oxide 0.47, desflurane 0.42, and sevoflurane 0.60. So at the end, it is necessary the elimination of the anesthetics if we want to recover the control of our brain once again. So it is necessary elimination by the lungs. Anesthetics that are high soluble in the blood are eliminated slowly. And in this phase, you feel this phase like hangover. So, and this effect remains for a long time, several hours, vomiting and so on. If the anesthetic is high soluble in blood. In contrast, anesthetics with the low blood solubility, such as nitrous oxide, are eliminated quickly, and the awakening is rapid, you see. Here you can see the chemical structure of these anesthetics. As I told you before, the most important anesthetics in the past were chloroform and the ethyl ether. And in addition, also nitrous oxide, NOS, N2O. In the past, this gas was defined as lighting gas. Because you know the delirium phase, and so the people can reach this phase by the inhalation of this gas. Nitrous oxide is still in use in association with other ether, while chloroform is toxic, the ethyl ether is flammable, and so no more used now. Here you can see the chemical structure of some recent anesthetics. You see all these three compounds are ether. You see the function, the oxygen function in the middle of the chain, with a lot of fluorine atom, which replace the hydrogen in order to decrease the flammability of this compound. Desflurane, sevoflurane, isoflurane, you see in the table here, sevoflurane, desflurane are the most common anesthetics used, actually used, together with the nitrous oxide. You see the name of nitrous oxide, lysine gas, sweet air, protoxide, and so other names. Very simple structure, 2 nitrogen and 1 oxygen. We can use also this compound in the engine. If you want to increase the potency of an engine, we can use this type because we increase the quantity of oxygen inside the cylinder. NOS, you see. But you see other, allotane, enflurane, isoflurane, cyclopropane, another gas, chloroform no more, chloroform can cause cancer, birth defects, other reproductive harm, you see. So it's toxic. And what about their mechanism of action? The scientists try to investigate how these compounds act on CNS. But at the moment, we have only indication about their activity on the GABA A receptor. Perhaps they are able to stabilize the open conformation of this receptor. And so we have a massive influx of chloride ions inside the neurons. So we have a depolarization, very low potential, minus value, at minus values of potential. You have a stabilization of the membrane of your neurons. This is an hypothesis. Another hypothesis is that these gases are able to disorganize the double layer of the neurons, of the membrane of the neurons, in order to stabilize the open channel form of other receptors with a massive influx of positive charge. So we have at the beginning a strong action potential, and then we have a plateau and a stabilization at high level of the potential of the neuron membranes. These are the two hypotheses. We don't know actually how, which of these two hypotheses is true or not. But the result is a stabilization of the neuron's activity. There are a lot of evidences about the interaction of this compound with the GABA-A receptor. In particular, the scientists used a photolabeled compound able to interact with some amino acids on the receptor, and they found this interaction with GABA-A by using this particular compound. But we don't know if the result is an artifact or not, because it's very difficult to investigate the activity of a gas. It's not stable. It doesn't remain in the same compartment, the same part of the membrane, so it's very difficult. However, some results were published, and in particular they found a specific site for allothane, you see, on a specific cluster, a specific cloud of aromatic amino acids. But in this case, the scientists used a very high concentration of allothane, and so perhaps the result is not true. We don't know. We know the final effect, but not the side effect, the site of the effect. Another hypothesis was formulated about the use of ketamine. Ketamine is used as an anesthetic, is able to block, you see, the channel of this particular receptor, and so to block the influx of sodium ions and calcium ions inside the neurons. In particular, on the nicotinic receptors. This is another hypothesis. The formation of NO, you see, is an important neuromediator. But only hypothesis. perhaps on the nicotinic receptor there is a specific acetylcholine allosteric sites. Okay, perhaps, maybe. So just an hypothesis. Intravenous anesthetics, liquid anesthetics, administered by injection. The most important is a barbiturate called thiopental. We have already seen this molecule, a very lipophilic molecule. Why lipophilic? You see on the skeleton of the barbiturate, a sulfur atom was introduced. Sulfur has a higher number of electrons, so is more lipophilic than oxygen. Thiopental is an ultra short acting positive allosteric modulator, ultra short. As I told you before, you are on the bed, they ask you your name, doctor asks you your name, and then you say, my name is Vincenzo, and then you sleep. 3 seconds, very, very quick. The second one is propofol, another well-known liquid anesthetic. Very, very simple, the structure. You see is a phenol, see an aromatic ring with an OH, and 2 isopropyl group in ortho position, sorry, on the 2 ortho positions. Is poorly miscible with the water, so you have to prepare an emulsion, and then you can inject this emulsion directly in vein. You have a very quick effect. So these are 2 important examples of 2 liquid anesthetics. Ketamine is the third. It interacts with the glutamate receptors. You remember that glutamic acid is an excitatory neurotransmitter, so ketamine is able to block the activity of glutamic acid. It's able to block the entrance of sodium and calcium ions inside the neurons. You see here the picture that we have already described before. Other 2 compounds which belong to the family of benzodiazepines are used as premedication. This means that benzodiazepines are not real anesthetics, but you can assume this compound before the anesthetics just to prepare your brain to the activity of anesthetics, and so the doctor can use a decreased concentration of anesthetics because you have already assumed benzodiazepines, which, as you know, they interact with the GABA-A receptors. In particular, 2 potent benzodiazepines. The first one is diazepam, called the Valium. It's very famous. And the second one is flunitrazepam, called the Rohypnol, another well-known benzodiazepine. So before the use of the general anesthetics, you can assume this compound just to decrease your anxiety, just to relax the muscles. At the end of this chapter, I want to describe you a particular technique that the doctors use when they have to make an intervention on the brain, directly on the brain. For example, a brain cancer, sorry. Because in this case, it is necessary the participation, the contribute of the patient. And so we have to avoid a general anesthesia. We have to control only the pain, and we have to control the reactivity of the patient. Because sometimes the doctor can ask to the patient to move, for example, the finger, to move the arm, to move the legs. It depends, on the district where they have to work. And so to avoid the severe damage on the brain, it is important the reaction of the patient. But we have to control the pain, and also we have to control a violent reaction of the patient. Please, doctor, no, this. Okay, you can understand. In this case, we can avoid the use of general anesthetics, but we can control the pain by a morphine derivative. I remember you, and we'll see in the next chapter, the use of derivative of morphine to control the pain. And also, we have to avoid a violent reaction of the patient by using an anti-schizophrenic compound able to block the forces, the muscle of the patient. A very potent compound called the droperidol. Droperidol is a dopamine antagonist, we'll see, able to block the willing of the patient, the forces, the muscle movements. So we can put together these two different compounds, and in this way it is possible to make an intervention directly on the brain. And we define this type of anesthesia as neuroleptoanalgesia. It is an important step in which you have the assistance of the patient during the operation. The patient is able to participate during the operation, you see. The level of anesthesia with this technique is comparable to the first stage analgesia, the first. Okay. Have you any question about this topic? At home? No? Here in classroom? Any questions? Before to start dopamine, I want to give you a brief description about fake news. Why? Because tomorrow, as I told you before, we'll have a seminar. Just a moment. Here. Okay. We will have a seminar about the bibliographic research, and we'll see how the scientific papers can contribute to avoid the propagation of fake news in the world, on the web, What exactly is a fake news? You can see here the definition. False, often sensational, information disseminated under the guise of news reporting. You see an illustration, an old illustration about the fake news. So it is not a modern concept. It was known also during the past. Fake news has been around for a very long time. You see, Easter 1475, a Franciscan preacher gave a series of sermons claiming a lot on news, fake news. Fake news pamphlets produced during the Lisbon earthquake. Benjamin Franklin created propaganda stories that the Native Americans were working with the British and scalping American patriots. Another fake news. It's an old concept. Pope Francis shocks world, endorses Donald Trump for president. You see another fake news. A lot. But why some people elaborate this type of news? Roll of paper, towels, signed by President Trump directly, just to make money. You see here, Rob Schultz makes a lot of dollars a month with the real news right now. Paris Wade and Ben Goldman made a lot of money about the presidential election. Because if a lot of people see your website with the fake news, you can hear money. And so this is the main reason. How to spot fake news? Can we control if a data, a news is real or not? First, what is the date of the item, on the item? All articles just lead back to one source. Does the news report come from a satirical site? Check all of the details. Check the image. Is it real and correctly attributed to the Photoshop? You know, where in the world does this happen? There is this particular approach, CRAAP. Currency, when was the information published or posted? Relevance, the importance of the information for your needs. Authority, the source of the information. Accuracy, the reliability. Purpose, the reason. This is an important approach. CRAAP. Look again. It's impossible. Sometimes we say, perhaps it's true. Check all the details. Who wrote the article? When was it written? Try a related. Try a link. Check on the web where the news is published. Photoshopped, so you have a lot of sites where you can see, you can check. For example, many people have cured their newly diagnosed cancer by using a very healthy diet and drinking a quart of carrot juice, but it's impossible. We have described the class of anti-cancer agents, and so it's impossible to treat a cancer with the carrots. Perhaps it's just a food supplement, yes, antioxidant, okay, but it's not possible to treat a cancer with the carrot juice. "64 people trusted the search engines, 57 trusted traditional media, 41 trusted social media." This is the number. The trouble with quotes on the internet is that you can never know if they are genuine. Abraham Lincoln, another fake news. You see Abraham Lincoln with a phone, mobile phone. Other, about COVID-19, a lot of fake news. You see, you have already seen on the web. Really, really a lot. How avoid fake news? How is possible? It is necessary to have data from experiments. So the scientific method is based on observation, question, research, hypothesis, experiments, collect data, analysis, and conclusion. When we want to publish some data about our scientific activity, the author prepares the manuscript, and then manuscript is sent to a journal. The journal editor checks, screens your manuscript. This means that the journal editor, a serious scientist, an important scientist normally, check the observation, the conclusion, and then, okay, could be. But if the conclusion are not true, seem not true. The editor can reject at the beginning your paper. Or, if you see the arrow, the manuscript can be checked by other anonymous scientists in the world. I send my paper, and perhaps my paper could be reviewed, you see, checked by other scientists in Africa, Australia, South America, I don't know where. Because the journal editor has a list of all scientists in the world which work on your topic. Normally, my paper can be controlled by 3, 4, 5 different scientists in the world. They check my paper, they make observation, this experiment is false, the data is not true, and so on. The reviewers, these scientists, prepare a report about their comments. Perhaps it is necessary to make another experiments. Perhaps it is necessary to add additional data. This conclusion is not true, and so on. At the end, the journal editor informs me about its decision. So you can understand that it's not so easy to publish a fake news using this type of approach, because the news are very carefully controlled by other scientists, by the whole scientific world, a scientist which works on your topic. The therapeutic activity should be demonstrated by by scientific papers based on scientific investigation. Material found in internet could not be based on scientific evidences. So it is necessary to check the papers. You see, Nature is one of the most important papers in the world. Neuroscience, cell science, and so on. And so tomorrow we'll have a seminar by Marta De Plan about Reaxys. Reaxys is an important software because you can use, you can search news on a specific topic, yes. For example, neurodegeneration, or by chemical structure. So you can put a chemical structure inside, and then you can choose, for example, side effects, activity on other targets, chemical physical properties, and so on. You see here the numbers, and really, I think it's important to know how the scientists publish their results, how the scientific community control the publication just to avoid the publication of fake news. Okay. Paper rejection. If they decide that your paper is false, data are not true, the paper can be rejected. And so you can receive phrase such: the study has not scientific significance, the study is not original, original. It is necessary the novelty. When you publish something, it is important the novelty of your paper. Not you cannot use data from another scientist or another people. You should be original. Suggested hypothesis was not tested. Erroneous methodology was selected. Violation of the planned method because of practical difficulty. Poor study design. Inadequate sampling. Results unsupported by evidence. Conflict of interest. You can imagine if Tumiati works in a company which works on neurodegeneration, I can publish some data about an hour compound saying that this compound is very potent, active, and it's the best seller. It's a miracle in the therapy. You can conflict of interest because I work in the same company and they publish the same. Okay, bad writing style sometimes. Okay, here you have the Peanuts, the comic strips. This is an example about the evolution of the news in the cosmetic field. Some years ago, the research on skin absorption was just an hypothesis. Now, recently, it is necessary to measure if a cosmetic compound is absorbed and to measure the effect, for example, on the wrinkles, on the skin wrinkles, if you want to write that this compound can counteract, can treat your wrinkles on the face, perhaps. This is the difference. In the past, okay, it's possible that this compound, maybe this compound act on. No, it is important to know the target and to have a clear effect. So picture about before treatment and after treatment of the skin. It is important to have this type of picture. Okay, this is just an introduction on the seminar of tomorrow. Have you any questions about this point? At home, have you any questions? Okay, we can stop for 15 minutes and then we will start with dopamine. Okay. Eccoci qua. Abbiamo aperto la dopamina. Fake news no, questa la spegniamo. Ecco qua. Allora. Perfetto. Ops. Okay. We start now with the new chapter of today related to dopamine and the dopaminergic system. Dopamine is an important neurotransmitter discovered only recently because at the beginning, more than 20 years ago, the scientists thought that dopamine was only an intermediate in the biosynthesis of adrenaline and noradrenaline. In fact, we'll see its chemical structure is very similar to the chemical structure of noradrenaline. They can act also, dopamine can act also on adrenergic alpha 1 and beta 1 cardiac adrenergic receptors, but only at high concentration. "30 years ago, the scientists discovered the existence of dopamine receptors, and in that time, they started with an investigation about the activity of this neurotransmitter on the brain. Possible I want to, it doesn't work. I want to show you a movie about dopamine, but it doesn't work. Ok, niente da fare. Lo stesso. Here in the picture, you can see the chemical structure of this molecule. It's very simple. Aromatic ring, 2 OH groups, ethylene chain, amino group. Very, very simple. Noradrenaline has another OH group on ethylene chain, close to the ring, to the aromatic ring. It is involved in 2 particular diseases. One is called the Parkinson disease, and the second one is schizophrenia. In the first case, Parkinson disease, we'll see that there is a degeneration of the dopaminergic neurons in substantia nigra, particular district of the brain. And in this case, we need agonists, dopamine agonists. In case of schizophrenia, we have an overactivity of this neurotransmitter in particular regions of our brain, and in this case we'll see we need a dopamine antagonist. So the two different phases of dopamine: Parkinson's disease, neurodegeneration of dopamine neurons, degeneration of dopamine neurons, and in this case we need dopamine agonists. Schizophrenia, we have to control the overproduction, the over-release of this neurotransmitter. In this case, we need dopamine antagonists. In 1979, the dopamine receptors were divided in two subtypes, D1 and D2. This means dopamine, D1 postsynaptic and D2 presynaptic, just to control the release of dopamine by negative feedback. At the end of the 80s, these type of receptors were cloned, and then we had in that type 5 subtypes, but divided in two groups, D1 and D2. Here in this picture, you can see the biosynthesis of dopamine and also its metabolism. Why it's important? Why are important these different pathways? Because in the case of Parkinson's disease, we have to increase the concentration of dopamine inside the synaptic cleft. For example, by increasing its biosynthesis or by blocking its metabolism, as you know. And so here you can see how we can apply these different strategies. The first one, how we increase the biosynthesis or by blocking its metabolism. The starting point of the biosynthesis of dopamine is an amino acid, very common, L-tyrosine. Tyrosine is an hydroxylated amino acid, you see. So there is already an OH group on the aromatic ring. It is necessary to add a second OH group in meta position, because in para position there is already an OH. And if we insert a second OH group, we have L-dopa. L-dopa is a tyrosine with an additional phenolic group on aromatic ring. After this reaction, it is necessary a decarboxylation of the acidic group to have dopamine. If we introduce a third OH group on the ethylene chain, we have norepinephrine. So in this pathway, we have the biosynthesis of dopamine, which in the past the scientists considered dopamine as an intermediate of this reaction of norepinephrine, which is the final point of the biosynthesis. How dopamine can be metabolized? Two main classes of enzymes. The first class, MAO, monoamine oxidase. Monoamine, this means that these enzymes are able to attack the monoamino function. Here you see the monoamino group, and to oxidize the carbon close to the amino group to an aldehyde, and then to a carboxylic group. So monoamine oxidase, MAO. The second group of enzymes able to metabolize dopamine is called COMT. COMT. C means catechol. Catechol is the aromatic ring with the two OH, two phenolic OH groups. An old nomenclature defines benzene with the two OH as catechol. O means oxygen. M means methyl. T means transferase. So this type of enzymes are able to transfer a methyl group on the OH, catecholic OH, in meta position. You see the result is this 3-methoxytyramine. 3-methoxytyramine is a dopamine with a methyl group on the oxygen in meta position. So, if we want to increase the concentration of dopamine in synaptic cleft, we can block MAO and / or COMT. This can be represent a strategy for the treatment of Parkinson's disease. But the problem is that if we block MAO or if we block COMT, we can increase, you can see also the concentration of norepinephrine, noradrenaline. So this strategy is not so selective because we increase also the concentration of other neurotransmitters, in particular noradrenaline. So we have an increase in heart frequency, you know, the activity of this neurotransmitter. Or we can have the increase of other tryptamine, serotonin, you know, other neurotransmitter involved in other functions. So we have other side effects. However, the inhibition of these two enzymes can represent a strategy. You can see that also L-DOPA, the first precursor of dopamine, which has still the amino acidic function, can be metabolized by COMT, for example, or can be deaminated by MAO. But why L-DOPA is so important? L-DOPA is the precursor, the first precursor of dopamine. Yes. Dopamine is not able to cross the blood-brain barrier. This means that if we have a neurodegeneration, a degeneration of the dopamine neurons in substantia nigra, and then we have Parkinson's disease, we can assume dopamine, but not orally, not by injection, because dopamine is not able to reach the substantia nigra because it's protonated here on the basic function, is protonated at a physiological pH, and so we have only effects on the peripheral receptors, which means that we have a strong vomiting effect on the stomach. We have a decrease in blood pressure, but not central effect. If we want to increase the concentration of dopamine inside the CNS, we have to administrate the precursor, L-DOPA. Why L-DOPA is able to reach the CNS and not dopamine? Also, L-DOPA has a basic function. Also, L-DOPA is protonated at physiological pH, but the difference is in the presence of the amino acidic group. And so L-DOPA can use a particular transport system necessary to transport amino acids inside the CNS. So L-DOPA can use this type of transport system, the transport system reserved for the transport of amino acids inside the CNS. So the strategy is, I cannot administrate directly dopamine. Okay, I can inject dopamine directly in the brain, but you can imagine it's not so comfortable. You have to cross the bones. So we can administrate the precursor, the L-DOPA. L-DOPA can cross the blood-brain barrier thanks to the presence of an amino acidic transport system. L-DOPA is able to reach the substantia nigra where it is decarboxylated to give dopamine inside the CNS. So you can see that this strategy is an undirected strategy. We assume a precursor, L-DOPA, to have an increased concentration of dopamine inside the CNS. Otherwise, we can inhibit the metabolic enzymes such as MAO, monoamine oxidases, or catecholomethyltransferase. We can inhibit these two different classes of enzymes. Dopamine is stored in vesicles. It is a typical neurotransmitter, with bivalent calcium ions. Why? We have to protect the two OH groups from the oxidation, because we'll see that dopamine is not stable because oxygen is able to oxidize these two OH to ketone. So we can have a quinone system, we'll see. So dopamine is not stable in the air. And so the chelation of these two OH with the calcium ions can protect the two OH group from the oxidation due to the presence of oxygen, in the air. Have you any questions about this picture? Is it clear? Yes? It is released by exocytosis, via calcium-dependent mechanism and so on. There is also an efficient reuptake in synaptic cleft. This can be important. Physiological role. Dopamine is an important neurotransmitter inside the CNS, but also the PNS, peripheral nervous system. In particular, inside the CNS, you can see the striatum, substantia nigra is a specific district rich in dopamine neurons. It is not clear why these neurons can go under degeneration. Only these specific dopaminergic neurons. Some scientists observed that in this region there is a very consistent metabolism of dopamine with the formation of a lot of free radicals. And as you know, these free radicals can damage important structure of neurons. But in this case, each of us should have this disease. It is not clear why only a small group of people is affected by this disease and other people not. However, one of the most important hypotheses is related to the formation of free radicals in this part of the CNS. Here you see a scheme about the formation of dopamine starting from tyrosine, you see, in the neurons, and then the release of dopamine inside the synaptic cleft. Here you can see how the receptors are distributed in the synaptic cleft. In particular, you can see D1 receptors in postsynaptic position, D2 receptor in presynaptic position just to control by negative feedback the release of dopamine inside the synaptic cleft. Here you can see also the reuptake through a dopamine transport system, a reuptake of the dopamine from the synaptic cleft. Dopamine receptors are involved in the fine control of the muscle movements. In particular, dopamine receptors are able to increase the activity of the muscle. But you see that these receptors are involved in other disorders, Parkinson, Tourette syndrome, tardive dyskinesia, Huntington's chorea, hyperprolactinemia, and so on. Here in the picture you can see the picture of Parkinson. Parkinson was the first person which described in the past 6 individuals with this type of symptoms. In particular, he distinguished between resting tremors and the tremors with motion. 2 different tremors. Parkinson erroneously suggested that the tremors in these patients were due to lesions in the cervical spinal cord, but in that time, it was impossible to have information about the CNS. Here you can see the regions involved and affected by Parkinson's disease. Pars reticulata, pars compacta, you see the different parts of the substantia nigra affected by this disease. In particular, you see that a lack of dopamine in striatum is responsible of Parkinson's disease. And then here you can see how dopamine is involved in schizophrenia. Schizophrenia has 2 different phases. Negative symptoms, the patient not willing, the patient remains without energy. And this negative schizophrenia is due by a deficit of dopamine in prefrontal cortex. But we are interested on positive schizophrenia due by an excess of dopamine in mesolimbic tract. Why? Because positive schizophrenia means violence effects. So we have to block these patients to avoid severe effects on parents, sons, daughters. We can see every day on the newspaper the effect of the positive symptoms of schizophrenia. So it is urgent to block the positive symptoms and then to try to treat the negative symptoms, but we have to avoid severe damage by this type of patients. So we'll see that antagonists of dopamine are used to block the effect, the violent effects of these patients on the people around them. So the two chapters on dopamine are divided. The first one on agonist, dopamine agonist, and the second one on dopamine antagonist. So we'll see these two different classes of compounds with the different effects. Agonists used to treat the Parkinson disease, and antagonists used to treat the positive symptoms of schizophrenia. Dopamine receptors, the two main classes, D1 and D2. In particular, D1 is, you can see two subtypes, D1 and D5, and in D2 like D2, D3, D4. But mainly, the main subdivision is D1-like and D2-like. D2 presynaptic, D1 postsynaptic. All these receptors are members of the G protein coupled receptor, GPCR superfamily, and consists of a chain of 387 to 437 amino acids. Once again, a dopaminergic synapses. D1 responsible for increased activity of adenyl cyclase. D2 a decrease of the activity of adenyl cyclase. In this table, you can see the 5 subtypes with their main characteristics and selective ligands, distribution, and so on. Here you can see once again how the dopamine receptor work with all the second messengers inside the neurons, inside the cells. Okay, here you can see a description of this figure. But perhaps you can find that you will see more details during the course of pharmacology. So it's just a description for you. Now, we have already described the importance of dopamine inside the CNS. A lack of dopamine in substantia nigra is responsible for the formation of Parkinson's disease. So, dopamine is not able to cross the blood-brain barrier. But also, dopamine is not stable on air. Easily oxidized the two catecholic OH groups can be oxidized to carbonate to give a quinone system. Dopamine is light sensitive, the same reaction by light. High molecular flexibility. Why we say high molecular flexibility? Because if you want to design selective agonist for this type of receptor, we have to know the active conformation of dopamine when dopamine interacts with the D1 receptor. And it's not easy. You see here the Newman projections of dopamine. The first form is one of the most stable conformation, is trans, you see, trans because you have the amino group in the opposite position respect to the benzene group, the aromatic group. Here you can see the ethylene chain. You can have a lot of different conformation, but one of the most stable is when the two bulky groups, the amino group and the aromatic group are in the opposite position. You see the structure from this point of view. You have here the ethylene chain, two hydrogen here, the other two hydrogen, these two, and then the aromatic ring. The other two forms, B and C, are in gauche. This means that the amino group is closed, more closed to the aromatic ring, less stable. And so perhaps we can assume that when dopamine interacts with the D1 receptors, probably is in trans conformation. A, the first conformation that you see here in the picture. But we have different trans conformation. It depends on the conformation of the aromatic ring. The aromatic ring can stay on the plane, like in this conformation, or perpendicular to the plane. We can decide that the dopamine structure can have a trans conformation and the aromatic ring can stay perpendicular to the plane, like in this form. But also in this case, the OH, one of the two OH group can be in a different position. You see, in this conformation is the same part of the nitrogen atom, or I can change the conformation of the dopamine of the aromatic ring, and in this case, the OH group in meta is in the opposite position of the nitrogen atom. The two forms are described here in the picture. The first one you see, the OH is in the same part of the amino group, and this is the second. The OH in meta is in opposite position respect to the amino group. So we can say that the active conformation is trans, okay, but we have two different types of trans. Alpha, when the aromatic rings stay on the plane, and beta, when the aromatic ring is perpendicular. So we decide that the trans beta can be the active conformation. Yes. Trans beta, you see the aromatic ring is perpendicular, but we have two types of trans beta. The first one, when the OH group is the same part of the amino group, and you see is the first, trans beta alpha rotamer is called. Or the second one, when the OH is in the opposite part. In this case, we have trans beta beta rotamer. Fortunately, we know the active conformation of dopamine, which is trans beta. This means that the aromatic ring is perpendicular. Alpha rotamer, where the OH is in the same part of the amino group. You see, this is the active conformation of dopamine. Trans beta alpha rotamer. But why? How it was possible to define that the active conformation of the dopamine at the target was trans beta alpha rotamer? This is the question. How we can decide that this conformation corresponds to the active conformation? We can perform conformational investigation by trying to identify the most stable conformation, but sometimes the most stable conformation cannot be the active conformation, because in the interaction of the neurotransmitter, in this case dopamine, the receptor, we have an interchange of energy, and we can have a movement, a change in the conformation of the neurotransmitter. Just a moment. No, okay. We'll see later, next time, not tomorrow, next Thursday. Fortunately, we have frozen analog, an agonist which contains the active conformation of dopamine. And so we can say that this conformation, trans, beta, alpha rotamer, corresponds to the active conformation of dopamine. This information is useful to design new and more potent agonists for the treatment of Parkinson's disease. Is it clear? Really? Oh. Good. Have you any question at home? Clear? Five minutes and then we stop. We have already described the active conformation of dopamine. Okay. The other problem related to the investigation to identify new agonists for the treatment of Parkinson is to have an animal model of this disease. The problem is represented that normally this type of disease appear in the old guys, in the old people, more than 60 years old, 80 years old. And so if we want to have an animal model, it was not possible. I cannot wait for a long time to have a monkey 80 years old. It's not possible. Fortunately, some years ago was identified a compound able to selectively destroy the dopamine neurons inside the substantia nigra. This was due by the design of a morphine analog by some students in university. So the next time I will tell you the history about the discovery of MPPP, which is a compound very simple with the same activity of morphine. But instead of this compound, the students synthesized a very toxic compound called MPTP, this compound in red. And this compound is able to kill selectively all dopamine neurons. And so we can have in this way an animal models in monkey. Okay. Have you any questions at the moment? No? At home, have you any question at home? So, tomorrow we'll have this seminar about the bibliographic research, and then in the next lessons, I will describe you the discovery of this compound able to selectively kill the dopamine neuron. Okay, dear students, have you a nice evening, and I'll see you tomorrow morning. Thanks. Ciao Caterina, ci vediamo. Ciao. Allora, ciao ciao.